We are very pleased to have Professor Feryal Ozel as our speaker today. Feryal is a professor at University of Arizona, which she joined in 2005. Before that, she did her PhD at Harvard University and was then a Hubble Fellow at the Institute for Advanced Study in Princeton. Feryal is recognized for her contributions in the field of compact objects. In particular, she contributed to neutron star and magnetar understanding of neutron stars and magnetars, including the theoretical interpretation of X-ray emissions from magnetars and determination of masses and radii to understand the equation of states. She, for these contributions, she received, among other awards, the Maria Goeppert-Mayer Award in 2013 and the Guggenheim Fellowship in 2016. She's also a collaborator on the Event Horizon Telescope that released the first image of a black hole. I don't remember if it was a year ago or 2 years ago with pandemic. And this is going to be the subject of today's talk. She's going to tell us what we have learned about the spacetimes of astrophysical black holes from EHT as well as LIGO and gravity. So take it away, Feryal.
Thank you very much. Thank you for the invitation. Lovely to see a lot of faces that I know and lovely to meet new people. So yeah, you're right. It's almost 2 years ago. It was April of 2019. We are all in a time warp. So I would like to tell you about what we learned from this black hole shadow that we detected in M87. So what I want to do is tell you a little bit about how the observations are done, what is the Event Horizon Telescope, and what is the methodology, how we reconstruct the image, and then tell you a little bit about what we learn about black hole spacetimes and what we learn about black hole accretion as time permits. So let me go ahead and get started with introducing the Event Horizon Telescope. This is the array in 2018. Since then, we have been able to add 2 more telescopes. But what this is a network of telescopes that's literally spanning the globe, doing observations at 1.3 millimeters, recording the data. And the key aspect of this is that we record the data from these various stations at the same time in order to do a technique or employ a technique called very long baseline interferometry. So what is that? What is very long baseline interferometry or aperture synthesis interferometry? It is a way of achieving high angular resolution with telescopes that are physically separated from one another. So it's not an interferometer where you actually have a cable running through. What you do is you look at a distant source, in our case, distant black holes, at the same time, record the data faithfully at the same time. And by faithfully, I mean we use hydrogen maser clocks in order to really time tag each arriving wavefront at our telescopes. And after the fact, take these large amounts of data, take them to correlators where we literally match up the incoming waveforms at 1.3 millimeters, 230 gigahertz. This is, of course, a lot of waveforms that need to be multiplied, and we get a signal. We get a combined signal as if the resolution that we had was from a telescope that is as big as the separation between the 2 telescopes. A little bit more about this technique. The reason I want to get into it is because I want to be clear about the nature of the data that we get, that what does interferometric data look like. Interferometric data basically gives us Fourier components of the 2D image in the sky. So the sky image is a brightness distribution in 2 dimensions. Each telescope pair will give us 1 Fourier component at any given time. For example, in this particular case, if I'm looking at these 2 telescopes, and I plot it as east-west and north-south spatial frequencies in the Fourier space, it's going to give me 1 point that corresponds to the separation between these 2 telescopes. So what we do is rely on the rotation of the Earth. The spatial frequency that we get from this 1 pair is L over lambda, where L is the distance between the telescopes and lambda is our observing wavelength. And as the Earth rotates, each pair starts filling out a little bit more of the Fourier space. But of course, when you have n telescopes, you have n choose 2 baselines. So you slowly start filling out the various Fourier components of the image that you're observing, and eventually get enough information about it that you can model what the brightness distribution in the sky looks like. Our primary targets were the supermassive black hole at the center of our own galaxy, Sagittarius A star, as well as the supermassive black hole in M87. Obviously, we have dynamical evidence for the presence of supermassive black holes at the centers of galaxies. And these two are the biggest in the sky in terms of their angular distance, angular size, meaning their the size of their horizon, which scales with their mass, divided by the distance to the sources. When you look at all the sources around you, including stellar mass black holes, and ask which one has the largest angular size, the black hole at the center of the M87 galaxy is one of them. So that was our primary target. As I said, it's been thought for decades to harbor a supermassive black hole. It has a jet associated with it, and we can also use this jet to say something about the inclination of our line of sight with respect to the black hole spin. So armed with all of that, armed with our array in 2017, we did the first global set of EHD observations, and you can see from the presence of lots of blue in these pictures that the weather was beautiful, and that's important because 1 millimeter actually gets absorbed by water vapor. So even though you can do observations during the day, the sun is not a problem on most telescopes. The amount of water moisture in the atmosphere could prevent us from observing. We got some beautiful days, and I was in this control center in Cambridge, Mass, where we coordinated the global observations. Let me also just flash a picture of what the EHD collaboration looks like. This is from our meeting in Nijmegen in 2018, as we were getting ready to publish the M87 results. So quite a large collaboration spanning all continents, in people as well as in telescopes. Actually, that is not true. We do not have a telescope in Africa just yet, but we have collaborators in South Africa. So I'm sure you've seen the tasty donut that all this effort led to. We had quite a bit of fun with it, but what did we actually learn from it? So in order to walk you through what we learned from an image of a black hole at what we call horizon scales, I want to tell you a little bit more about how we actually reconstructed that donut, what it is that we can definitively say about it, and what we can learn about the space-time using that information that we have confidence in. This is the same Fourier space that I already showed you, just east, west, north, south, if you want. And these are all the telescope pairs that gave rise to these tracks on the Fourier space. So obviously this is a 2D image, but if we just go around and take all the angles and plot it as a one-dimensional amplitude versus spatial frequency on a figure like the one on the right, what we see is this type of shape, okay? So for example, if we had azimuthal symmetry and we did collapse it all into 1D, what you see is in the Fourier domain, a ringing, what you would call a maximum, a minimum, a maximum, and potentially headed towards a second minimum. This type of ringing is very characteristic of a structure, first of all, a compact image, and a compact image with sharp edges. So it could be a disk, it could be a ring, but this is a Bessel function, basically, and obviously we can model it at different azimuths differently. But to 0th order, when you see something like this in Fourier space, you say, ah, I'm dealing with a Bessel function. So what that allows you to do is basically identify the salient features of the visibility data. What is it that these data are telling us in terms of the underlying structure if I could model it with some analytical function? This is not all we do, as you'll see in a minute, but if in the image space my brightness distribution looked like this, in the Fourier space, it would correspond to this green curve that you see on the right. It's not a good fit. It's actually pretty terrible. Nobody would say that the green describes the red points, no longer color coded. So let's put all the telescopes in one go. So what can I do? Well, what the two things that I can change about this is the size, first of all. And we know from Fourier transforms that the location of the first minimum determines the image diameter. This is 50 microarc seconds for reference. Okay, 50 microarc seconds of angular size in the sky. Okay, now we're doing certainly better with this part. We're absolutely not doing better with this part. What is something else that I can change with my image in order to get the right form of the Bessel function? I can change the width. So a filled disk cannot describe the Fourier space data that we have, but a ring-like image can describe it much better. Okay, so this is what gives us confidence that there is a hole at the center. This is still not a good fit. The reason is that in this mock picture that I'm showing you to develop this understanding of visibilities, the Fourier space data, I assumed at this point, I assumed infinite resolution. EHT does not have infinite resolution. Our largest baseline is the size of the Earth. So if I now blur this using a Gaussian to the resolution of the EHT, then you say, yes, of course, this is a much better fit. This is the basic idea behind this donut that we have. This is azimuthally symmetric. You see that these data are not. So going in, the fact that we have collapsed all angular directions into one direction does not do it justice. So we will need more sophisticated models like crescents and image domain techniques in order to find the full structure. So we've done that. We've also had lots of work done in the imaging working group where instead of assuming an underlying analytical function that the data is kind of screaming at you, we can also build pixel-based models where you divide up your space into n² pixels and you allow the brightness to change independently. But with something called a regularizer. So I will show you an example of that. Basically, you minimize a chi-squared that's not just data minus model over error, but you also put a weight to a regularizer, meaning pixel to pixel variation gets penalized if it's too large. So assuming some smoothness of the image, you build a forward model of your image space. So I will show you how that works, this chi-squared minimization using the animation that you see here. These are, again, north, south, and east, west baselines. So one of them is doing a good job of getting this minimum, and in the other direction, the minimum is not as deep because of the asymmetry in the image. Okay. We have done all of this, and at the end of the day, that gave us confidence in this image and the visibility domain constraints that we published, basically saying that it is a ring-like shape. There is a north-south asymmetry present in that ring-like shape, which we associate with the Doppler shifts of the plasma surrounding it. So in this particular case, the plasma at the bottom is rotating
Feryal, you cut out for one second or a few seconds.
Explains the asymmetry. Yeah.
Feryal, we lost you for the last 10 seconds or so.
Is my connection okay, by the way?
Most of the time seems okay, but maybe turn off the video might help.
We lost you when you started to talk about the asymmetry between south and north and the Doppler shift.
Yeah.
Hello.
We
Hi.
can hear you again. Yeah.
I don't know if you can hear me. The video feeds that I'm getting are frozen and I can't hear anything. So I'm just going to give it 30.
We can hear you.
We can.
I can hear you. Yeah, we can hear you. And yeah, if you want to restart this slide, we lost you when you started this slide. We can hear you, Feryal. I don't know if you want to keep going or.
I will send her an email quickly.
I still can't hear anything, unfortunately.
Oh, okay.
I just heard you now. I heard you say, "Oh, okay," but I heard nothing for the past minute and a half before that.
I see. So can you hear me now?
Yes.
Good. So yeah, we can hear you. We lost you for a minute or so for the last slide, but we can hear you fine now.
Just give me 1 minute. Let me see if I can get my kids off of their Google Classroom or Zoom or whatever they're on and see if that improves my connection.
Okay, yeah, we'll wait. Sorry about that.
So I've been actually using Google Meet for a panel last week, sharing a panel, and actually Google Meet is very smart. It notices when your connection is bad and it turns off other people's videos for you. So actually I was really happy with that aspect.
I think Zoom compresses everyone else's video stream, but not your own, not the speaker's screen. Mm-hmm. So sometimes turning off your
yes, that's right. Yeah, it helps to turn off the one-on video or other people's videos. Then.
Hi, Feryal. Now it looks like
being able to hear you. So can you tell me if you're able to hear me?
We can both hear and see you.
Feed also choppy.
We can hear you fine. Your video is a little bit choppy, but the audio seems to be okay. So we lost you at the north-south asymmetry.
Okay, you hear me. We lost you at the north-south asymmetry. Okay, wonderful. Thank you. So I am going to keep going, assuming that my feed towards you is fine.
Okay.
Okay, so the image elements that I was describing are this flux depression at the center that we are associating with the black hole shadow, this brightness that we do see, which is the only thing that we can actually record, we don't have a direct way of looking at the shadow, which is the emission from the surrounding plasma, or we are associating with the emission from the surrounding plasma. And I was mentioning this north-south asymmetry, which comes from
Sorry, Feryal, we lost you again.
Team, maybe you should advise her to switch. Oh, Feryal, if you could switch off your video, that may help.
Please. Yeah.
Would it help if we switched off ours or not?
It might,
like
yeah. Let's all
Maybe
do
it's
that.
better. Yeah. Okay.
Feryal, could you please turn off your video and reshare your screen? Maybe that will go a bit smoother. I'll pause the recording.
okay, and
Everything's great right now.
sounds good. So should I try to keep my video on or not try?
It's fine. It's fine now. I'll
It's fine. Okay. If it becomes a problem, and I'm not sure how I'm going to notice it with your videos off, but
I will send a message in the chat then if it's bad again. Okay.
the only problem is when I'm on full screen, I can't see the chat. Could you send me a text if that happens?
Sure. Got it. Thank you.
Okay, thank you. Sorry about this. It usually doesn't happen, but of course, when you're giving a talk, it happens. All right, so should I do the image elements again or just move on to what we can infer from it?
Hey, you just mentioned the north-south asymmetry due to the Doppler shift. That's where we lost you.
Okay, great. So the other thing that we infer is the flux depression at the center, which we associate with the shadow of the black hole, where light is being no longer gets to the observer. And of course, the thing that we actually see is the narrow ring of emission from the surrounding plasma. That's what our telescopes are able to record. We associate this, this ring that we see with the emission and the absence of this light at the center, that hole that I showed you in the models with the black hole shadow. So how do we make progress as far as turning an image like this into a metric test of the black hole, or further understanding about the ring of emission from the plasma? At this point, these two are actually orthogonal goals. So I'm going to try and take you in two different directions. If our goal is to understand the space-time, the question that we ask ourselves is what's the minimum that we need to understand about the plasma in order to reach conclusions about the space-time? Basically, does it depend on very detailed models of understanding a turbulent accretion flow, or are there things that we can say about the Kerr space-time of a black hole, for example, without having to do that? Having said that, our second direction is there are, of course, a lot of rich physical phenomena that happen around astrophysical black holes. The plasmas are low density, low luminosity. We model them with general relativistic magnetohydrodynamics. That itself probably is not enough, as I will try to show you towards the end. So what is it that we can use observations of this type to understand about accretion itself? So the outline of the rest of the talk is I'm going to talk about what GR spacetimes imprint on the image. Then I'm going to talk about how we model the plasma around it and what is the basic that we can take away from it, and then additional phenomena. So the reason why we have embarked on this imaging journey with the Event Horizon Telescope in the first place is because black hole spacetimes have characteristic radii that gets imprinted on the images that you make of their surroundings. The three characteristic radii that are most important here are, let me start with the photon orbit, the distance from the black hole at which photons can make a full circle or multiple circles. So it's the separatrix between photons falling in and are able to come out. Interior to that is the event horizon. And what we're plotting here on this graph is the radius in units of black hole mass as a function of the black hole spin, because all of these characteristic radii have a spin dependence. So for example, the event horizon is at 2m for a non-spinning black hole and at 1m for a maximally spinning black hole. This is the photon orbit. And then there is this characteristic radius called the ISCO, innermost stable circular orbit, at which point there are no longer circular orbits for matter, and matter loses angular momentum support and falls in towards the black hole. So the effect of all of these characteristic radii is that they imprint these characteristics on the photons that are generated in the vicinity of the event horizon and affect the images that are associated with it. So to give you a little bit more about what the photon orbits look like around spinning black holes, these are two different black hole spins in dimensionless units. And these are animations from Leo Stein. What you will see here is that photon orbits, even though they precess in spinning spacetimes, they trace out spheres, which look to us like circular images. So when we try to map the spacetime into certain characteristics of the images, there is significant gravitational lensing. And based on the impact parameter from the center of the image, a particular photon that reaches an observer at infinity has traced out a different path length. The ones, so let me just mark these now on this two-dimensional image. This is the photon path, and this is going to be the impact parameter as I move this towards the right. This is our photon orbit, and this is our horizon. So what you will see is that at different impact parameters, an observer at infinity, let's put our screen to where at the bottom of the image here, and what it will see is photons that have traced out different orbits in the space-time and therefore have accumulated different brightnesses, assuming the emissivity is uniform for the time being. So when I run this, what you will see is that the ones around the photon orbit, now more slowly, have a significantly larger path length than the ones that are further out. So if I now do a static of this, basically ask, where are these photons coming from? Where are these photons coming from? As you can see, the ones that skirt the photon orbit come from all of these directions that suffer very large amounts of deflection, and correspondingly, their path lengths are much, much, much larger. So this is the demarcation between what you see from a black hole and what you don't see. And interestingly, as you will see in a minute, because of, even though the photon orbit itself shrinks in a spinning space-time, because the lensing is stronger, this separatrix is going to be in the same place. And photons further out come from paths that have deflected a little bit less. I can also stop for questions, so please try to grab my attention if I can explain something in more detail. what I'm describing to you are all Kerr black holes. So the space-time's characteristic radii and image formation in Kerr black holes. And when all is said and done, when we look at image sizes that we expect from these space-times and the shadow shapes that we expect from these space-times, they show a particular size and symmetry. So to illustrate that, here I'm going to change the spin of the black hole. This is an animation from my former graduate student, Leah Medeiros, who's now at the IAS. And what you will see is that if I change the spin of the black hole up to maximal spins, about 0.99 and change, even though the entire image moves, its shape barely changes. It's only at maximal spins that I start seeing that flattening on one side. I'm not going to show you the animation for the observer's inclination, but the same thing happens with observer's inclination. Changing it has a minimal effect on the size and the symmetry that you expect from a black hole image. That is great news because we don't know spins of black holes a priori. We don't know our line of sight with respect to the spin axis of a black hole a priori. But if these have a minimum effect, plus or minus a couple of percent around this magic radius 5 that I showed you in the previous slide, as I change the inclination and as I change the spin, if I make this minimal change in the size and the symmetry of the image, and of the shadow, then I can use this as a pretty clean test of the space-time around the black hole.
Feryal, to what
Yes.
to what extent does the plasma affect the shape of the image?
Very good. That's where I'm headed. Okay. I'll show you just a couple more things before answering that question about to what effect does the plasma play a role. And the additional bit that I want to show you is that when you change the space-time around the black hole, so you go to a non-Kerr metric, whether this is coming from a particular theory of gravity, or you just want to be able to parametrically deviate from Kerr so that you can do tests of how much can I deviate? What are my predictions if I'm not Kerr? Because if I change all these parameters and I still get the same thing as the Kerr metric, then it's not a good discriminating observation between Kerr versus not Kerr for the black hole spacetime. So here are two examples. We've explored quite a few. This is the Johansson-Psaltis metric with its parameters of how to deviate from Kerr. This is the MGBK, the bumpy Kerr black holes, with its perturbation parameter for different black hole spins. The takeaway message from this is not how to modify gravity. There are entire talks one can give on that, but that in non-Kerr spacetimes, in deformed Kerr spacetimes, the predictions deviate for size and symmetry, deviate significantly from Kerr. So it's actually, it allows us to use EHT as a good test of the metric because of that. The other good news is that even though overall the shadow size and symmetry deviate, again, there is a very weak dependence on black hole spin. So you can constrain deviation parameters from GR without knowing the spin of the black hole. One last thing that we noticed, this is from our recent PRL paper, the parameters that affect the shadow size are primarily in the time-time component of the metric, which allows us to do good comparisons with other tests that measure only the time-time component. So with all of that, the claim that I'm going to make, and I will try to support in a few minutes, is that black hole images trace out the space-time. So to what extent does the plasma affect this, the size of the ring, the location of the ring, and the width of the ring? And here are electron temperature parameters, which are of no importance for this talk. But the takeaway message from this is that the brightness profile always extends down to the shadow, and that as long as the images are thin enough that they're consistent with our data, that the peak of the brightness, the peak of the emission does not deviate from the shadow by more than 10%. So I will try to make this point more clear, but if you believed that the space-time is written into the images and the plasma does have an effect, but that as long as they are ring-like and narrow, the emission does trace out the outline of the shadow with a bias parameter that can be quantified and with an uncertainty that can be quantified, then we are in business as far as doing a metric test of general relativity.
There's a question from Mariam.
Go ahead, Mariam.
Yeah, so just coming back, I mean, you showed us very nicely the simulations that spin does not influence both in the Kerr and the non-Kerr metric, the image you see. But I was wondering, is there kind of a intuitive, I know it's always hard to talk about intuition with GR, but is there an intuitive reason why not? Because, for example, for ISCO, right, that is very sensitive. And of course, if you work on stellar mass black holes, right, that you've also worked on, where you're using the accretion disk, in a certain state to constrain the spin of the stellar mass black hole. That's been very important and impactful. So I'm curious, is there kind of an intuitive reason why for this kind of work the spin does not influence the
Yeah, there is, and maybe I can try to answer it at multiple levels. The simplest way to describe it is that even though the photon orbit moves deeper into the potential, the lensing of that orbit to the observer's plane basically cancels it out. So we call it a fortuitous cancellation. I don't know if there is a deeper reason why both the frame dragging and the quadrupole and this just the lensing that you get from the TT component simply gets undone as you go to higher spins. Maybe there is, but ultimately that's what happens. That you move in deeper into the potential, but the lensing brings it right back to no, the image that you're going to see is going to be at 5M.
Okay, thanks.
So again, in this framework that I described to you, we can then use the black hole shadow that we infer from the image to go to a mass. We had outlined this in an earlier paper. Basically, you measure image diameter, you do this in the imaging domain, and you do this in the visibility domain, any reconstruction technique that you want. You calibrate the diameter to shadow size, which is what I was just telling you. The brightness profile truncates at the shadow, but its peak can be somewhat displaced. So we use a suite of GRMHD simulations for this, and we convert the shadow size into a black hole, allowing for this uncertainty in the black hole inclination and spin, which is this very narrow range, as we were just discussing. So if I know M over D through independent means, I have a unique prediction for the size, and then I can compare that to the size that I'm measuring. Alternatively, if I'm measuring a size, I convert it to an M over D and compare that to prior measurements. This is what we had done in the first set of papers. M87 has two sets of measurements for its mass, coming from the dynamics of stars that are far out and the dynamics of the gas that is far out. And these are discrepant at the levels that you're seeing here. And what we're plotting here is the probability density over this M over D parameter coming from these dynamical measurements. So let's put what we get from the EHT on top of this. And there is, because of the resolution issue, like understood resolution effects, There is a slight difference between fitting crescent models and fitting image domain. These are the two measurements that we get for the, sorry, this is the measurement that we get for M over D using crescent models. As you can see, it is really close to the mass inferred from stellar dynamics, the M over D, so that if we now turn it into a, is our size consistent with what is predicted from GR, and write it as a fractional deviation, it is highly consistent, 0 plus or minus 17% for the stellar dynamics measurement, and it is it has some discrepancy of order 50% with the gas dynamics measurement. In recent work, as I said, we didn't just ask, are we consistent with GR? We were also able to ask, well, how different are you allowed to be from GR? So using these modified Kerr metrics, can you actually constrain how different you can be and still be consistent with the predicted size of the black hole shadow and image? So this is from the recent work by the collaboration. And these are these deviation parameters as a function of black hole spin. When we do this numerically, we can do the full spin solution. We don't even have to assume that, that there is no spin dependence. But as you can see, the analytic limit actually does a pretty good job of recovering that here and here. So we were able to put limits on deviation parameters in the time component of the metric that is 500 times better than any previous test. And the best one so far were the solar system tests for that component. Okay, so how am I doing with time? Oh, I'm doing so-so. Let's come back to this question of, well, how much does the plasma affect what you're saying? What do we do to understand in more detail images around black holes? What we do is we solve equations of magnetohydrodynamics in Kerr spacetimes. That's why it's called GRMHD. And using these codes, we explore a variety of initial conditions, meaning we feed disk from large distances, we vary black hole spins, we vary mass accretion rates, we vary initial conditions of the magnetic field geometry that can thread the disk, and of course, let the magnetic field evolve because these are MHD equations. And we also explore different particle heating scenarios in which the electrons and protons get different levels of energy as it cascades down to small scales. And in order to do all of this, we use large-scale computing resources, running simulations of this type for a long time so that they reach steady state. The initial phase no longer matters. And we explore these large parameter spaces, including observer's inclination, et cetera, et cetera. So this is just an example. I know there are quite a few among you on the call today who have worked on GRMHD and beyond. So this is just meant to be an example from Oleg Sadowski from our previous NASA TCAN network when we were working on these flows. Then we still have to convert parameters like density, magnetic field strength, temperature to actual observables like spectra, light curves, and of course images. So we do GR ray tracing. This is an example from CK Chan, who's an astronomer here and actually my former student more than a decade ago. And this is a GPU-based code that he had written that allows us very efficient rendering of these many frames of GRMHD into the observer plane that you see in the distance here. And we can trace out basically for each of these impact parameters through the 3D flow, what the observed image and spectrum, et cetera, would look like. So we use these and the Event Horizon Telescope collaboration, especially the theory and simulation working group and entire working group, invested a huge amount of effort and time to really explore this wide parameter space as well as the unknowns in the plasma physics. So what if the electron heating is different than what we thought? What if the development of turbulence is different than what we thought? What if the magnetic fields arrest the disk, the MAD configuration? What if, lots of what ifs. So this is just a little portrait gallery from the simulations that we have worked on. And what you're seeing here is that there are some thicker disks, but in each and every one, the photon orbit is lit up and the brightness profile basically just traces out the plasma around it. So in each one, and this is partially where our claim is coming from, in each one where the thickness is comparable to or even like half the thickness of the ring is less than half the radius of the ring, then we can confidently convert the space-time characteristic, which is the shadow location, to where the emission occurs. Now, you might look at this and say, wait a minute, first of all, you're doing GRMHD, which means you're baking GR into what you're doing. So then how can you turn around and do a GR test? You might be thinking, what if MHD is not a complete description? And you might be thinking, at least some of you who work in nearby fields, I'm pretty sure I have seen pictures in the literature where the ring was at the ISCO, not at the photon ring. So can you help me reconcile those things? So if you're thinking any one of these things, you're in luck, because I would like to show you that the results are insensitive to details of GRMHD. This is some recent work that we've done, we're about to publish. What we basically said is that take any reasonable velocity and density profile. So radial velocity of the theta and phi components of the velocity, and any reasonable density profile. For visuals, what I'm showing you here are 3 different snapshots from one particular simulation of a magnetic field configuration and spin, but ultimately it doesn't matter. As long as we know that accretion disks happen, and accretion happens because matter loses angular momentum and subsequently moves into smaller and smaller radii, eventually crossing the horizon and becoming part of the black hole. Even if there are outflows here, take any reasonable velocity and density profile, and in the inner disk require only continuity, and that the particles move on geodesics. Geodesics of either the Kerr spacetime or your non-Kerr spacetime, if you are working in non-Kerr. So that's what these dashed lines are. So extending all of these density profiles interior to the ISCO, excuse me, requiring that matter doesn't disappear. I think as physicists, we can agree on that. And that we are not losing the geodesic character of our spacetime. When that happens, again, you recover images where the brightness truncates at the photon ring, as you can see here. And there is certainly a brightness profile outside of it. These are 2 cross sections of the image on the left, vertical and horizontal, but there is no hole. The only way to make a hole, and the only way holes have ever been made in the literature, is you take what you consider to be your sensible density profile that requires continuity, and you basically forego it. You set it to 0 interior to the ISCO. Then and only then can you displace thin rings from the photon ring, as you can see here, basically make additional peaks in this that are artificial. I am willing to bet that this is not something that we're willing to consider as far as reasonable plasma model. There is actually a second way the image can be displaced from the shadow. For completeness, let me mention that. It is when there is a, for example, a flux tube or a density perturbation actually crosses a caustic. So it goes behind the black hole and makes this beautiful Einstein ring, but these are short-lived. So as soon as I start, I on purpose started the movie there, but as you can see in a couple of dynamical timescales at most, this disappears. So if we happen to be so lucky that the image that we saw is actually an Einstein ring of a fluid element that's crossing a caustic and brightening, then obviously subsequent observations are going to help us address that. Can I answer any quick questions before I move on to the very last few slides where I talk about more fun things about the accretion flow?
I'm curious about the time scale of the variability compared to that of observations. I don't have the numbers. Maybe it's completely different.
It's not. Very good question. Okay, so let me, oops, sorry. Let me go back here and might as well just leave this movie going. So the fastest time scale that we need to worry about is the orbital time scale here. And so for Keplerian orbits, for M87, because it's 6 billion solar masses, depending on the spin of the black hole, it can be as short as about 4 days, and it can be as long as months. So during one night of observation, we are fine. As we are doing these scans waiting for the Earth to rotate, we don't expect significant structural changes, but our observations spanned a course of about 10 days. So from the first night to the last night, in principle, we could have seen structural changes, but even though we didn't publish the paper, let me go ahead and tell you we don't. We don't see significant structural changes. Sgr is a different story, and that's the reason why it got put in the back burner, even though Sgr's mass determination is much, much better than M87, and we always thought we would publish that first. It's only 4 million solar masses, which means the dynamical time scale, depending on spin, is minutes to a day. It's like many hours. The assumption that the source sits still during the scanning is no longer valid. So the variability aspect of Sgr has been more challenging to deal with.
And when you say that you know that you haven't, there's no variability in the source, is there's closure relations, is that right? That you can check some relationships between the visibility coefficients? Okay. Because technically, otherwise you could have different visibilities representing the image at a different time, but you say you can actually check this explicitly.
Indeed, that's, okay. So I didn't get into those details in this colloquium, but even though we lose absolute phase, we can reconstruct what are called closure phases, basically using 3 triangles where the phase delays cancel out. And that tells you directly something about the structure of the image. And by looking at the change in the closure phase over individual nights and from night to night, we come to that conclusion. Other questions? Okay, in that case, I'm going to try and just wrap this up in 5 minutes, but I think it would be a disservice if I led you to think that, look, we do all of this GRMHD work, and then we do the semi-analytical work to understand what we can trust and not trust, as if there isn't richness in the plasma considerations itself. So what I want to do is just tell you a little bit about, give you a flavor of the open questions in black hole accretion flows and the new directions that a lot of us are embarking in GRMHD and beyond. The difficulty about accretion flows like the one around Sgr A and like the one around M87 is that the thermalization timescales that rely on Coulomb collisions are much longer compared to the accretion timescale. So the mean free paths are basically larger than the size of the accretion flow. So you can't rely on typical thermodynamic kinetic arguments to say, oh, I have a thermal plasma and the equipartition of energy, et cetera, et cetera. What that does is that it makes particle heating challenging to understand from first principles on this type of accretion flow. And it most likely implies, because thermalization time scale is long, the presence of non-thermal particle energy distributions. So another thing that we see in ideal GRMHD simulations is that there is flipping of the magnetic field on short length scales, probably accompanied by large current sheets. So if we infer the current density, even though these are not resistive MHD simulations, what we see is there's magnetic field flipping in the phi direction and infer the presence of current sheets. So these are prime locations where the magnetic field can actually reconnect if we had allowed it to reconnect, which ideal MHD doesn't, and accelerate particles. So coupled with the long thermalization time scale, this is making the thermodynamics of the plasma quite interesting. Why do we care about this? Well, we knew that the effect of the particle distribution affected the image size from one of the first times we worked on this. This is my first paper on this, on black hole image sizes from 2000. And you can see already a thermal and a hybrid thermal, non-thermal distribution. And we were worrying about whether this would affect our 1 millimeter observations here. We've come a long way since then. We look at the effect of particle distribution on image sizes. This is from Mao and collaborators in 2017. You can see that a significant fraction of non-thermal electrons can change the opacity in the flow and the amount of emission that we see in the flow. In this particular case, this is a spatially uniform distribution, so even a small fraction makes a big difference. But when we come to Sgr A, actually, there is persistent variability as well as flaring in all wavelengths at which we observe that source. So this is Spitzer, this is Keck, infrared observations, this is Chandra, X-ray observations. You see these rapid increases repeatedly, about once a day, in the count rate, and some of them are very, very large, that happen at these multiple wavelengths. So, and some of about a quarter of the infrared flares are coincident with the Chandra flares. You may have also seen the recent beautiful work by the Gravity collaboration, where they actually spatially resolved the location of the flare and followed it for what they called an orbit. It may not be an orbit, but nevertheless, it's motion in the accretion flow. So clearly, there is some level of particle acceleration happening. These rapid increases in intensity are happening. And if that's the case, then that's also going to affect, on at least during these flares, the image size and scale. So the ways to move forward are, I just want to show you some recent work from Bart Ripperda and collaborators. Doing these global simulations, we can move towards resistive MHD. And what is nice about their work is that they have coupled it with adaptive mesh refinement, so that when we look at density, temperature, and this inverse plasma beta parameter, which is basically magnetic energy to thermal energy, what you see is that things that we were not able to capture in ideal MHD, such as these reconnection sites and current sheets, are becoming more and more obvious. Look especially at this one, where you see these beautiful little islands forming. These are potential sites of magnetic reconnection. So they can artificially increase resistivity here and identify how frequently does this happen, how big are these plasmoids that form, and what could the effect on the large scale flow be. Another direction that we can go to is fully kinetic. So abandon the fluid description altogether, but of course this is extremely expensive. I'm trying to keep track of particles and then depositing their fields on a grid, interpolating. So it is a complete solution, but it's impossible to do on accretion flow scales. So this is some work. Again, the slide is from Bart, but some plasmoid formation work through the stirring instability and how they grow and merge and potentially give rise to these sites of particle acceleration. So the work that we have embarked on with David Ball, my graduate student who just finished, and in collaboration with Lorenzo Cironi, is try to understand how particle acceleration would proceed during reconnection if we took basically some guidance as far as what betas and densities, et cetera, we should be worrying about from global simulations, but set up pick on a much smaller scale so that we can really understand the formation of these plasmoids through these instabilities, and then how they subsequently merge, and how this current sheet evolves. The advantage of doing this is that we can then, of course, not only put tracer particles and look at how individual particles get accelerated. So this is the Lorentz factor. This is the non-ideal field associated with the reconnecting field. So as you can see, this little particle, as soon as it goes through one of these regions of a large non-ideal electric field, it gets a kick, and it subsequently bounces around in these plasmoids to get more and more energy. And what that does is it produces a non-thermal tail in the electron and proton energy distributions, which I'm not showing here. Okay, so that's what I wanted to show you today. Basically, the takeaway message is that we already have robust results from image-based metric tests as applied to M87. We can separate out the uncertainties coming from the space-time from the uncertainties coming from the plasma. At some level, that's still the dominant source of uncertainty. However, we have other tools that we are relying on, and I will just say stay tuned for those. For example, we have M87 polarization results coming out soon. That is a unique probe of plasma properties in addition to the total intensity that I discussed today. So this is a polarization map, entirely theoretical, from Jason Dexter, his work in 2016, including the various effects like rotation and absorption, polarized radiative transfer. So polarization, in addition to the intensity maps, is going to give us a new handle. And obviously we have some work on Sgr A coming out, and some interpretation of flares and variability will give us more insight, hopefully, into what the plasma is doing, and eventually coming up with better first principles simulations for that. I will stop there. And sorry about the connection issues. Hopefully you were able to hear the second part better.
Yes, it went great. Thank you for a beautiful talk from everyone. yeah, if you have questions, please raise your hand. It's under reactions. And I believe Glennis had one, or sorry, no. Yes, oh, sorry, these are clapping. It's hard to tell.
Oh, sorry,
Okay.
I did have a question, but Glennis, I think, had one too.
No, I just
You know.
actually, well, I had a talk, but a question, but I think you basically answered it. And I mostly wanted to clap and thank you. It was just wonderful, Feryal. It's beautiful.
Thank you, Glennis. I appreciate it.
Yeah,
Shall I go?
Yeah.
So I
yeah.
wanted to ask you regarding the variability, Feryal, since you pointed out the timescales are a few days to a month. Would it be useful at all to redo an observation of M87 in intensity, you know, a year or two later, you know, redo the same thing and just have a different image at a different later on in time?
Absolutely. And if you know anybody on the ALMA tag, please tell them that it would be extremely useful. So we have 2018 observations that we started looking at in parallel to 2017. But it's basically limited person power, looking at polarization, looking at Sgr A, looking at multi-year data. But our 2019 observations were canceled because of technical problems, 2020 because of COVID. So at the end of March this year, we are hoping for a good observing run where absolutely, you're right that repeated observations on year time scales, it could be sensitive to small changes in the mass accretion rate. You could catch it at a slightly different state, or simply extend the baseline that where you can see these day-to-day variations on the M87 dynamical timescales. For Sgr A, of course, it's even more important because our 2000, I don't think it's any secret that our 2017 data does have a Chandra flare in it. And before and after, there are things that are happening. So looking at it both in more quiescent states and maybe catching other flares and variability timescales would be absolutely very useful.
Mariam?
Yes, thank you so much for this wonderful talk. I had one question about, so M87 has a jet, right? And we know the direction of the jet. Was that ever considered? I mean, you know, that was the cool thing about before this beautiful work is that we could see where the jet in 87 was VLBI, right? Where it originates, which of course is much further out than what we can see. But is that, I seem to remember there was some constraint on some models, right? There was the constraint used for the jet direction.
Absolutely, yes. So there are definitely longer wavelength VLBI observations of this jet, and there's nice structure that we can see. So what we were able to say here is that, first of all, we could use that jet direction as a constraint on the observer inclination. So basically assume that the jet is aligned with the spin axis, and if so, the observer inclination would be, I forget now, like 17 degrees, 21 degrees, something like that. But the other thing that we were able to do is use this asymmetry in the image and say, if that is aligned with the spin axis, so the directionality of if the angular momentum vector of the flow is aligned with the spin axis and it's coming towards us at this bottom brightness, then does it match the spin direction inferred from the jet? And yes, they are coincident.
Any other questions for Feryal from graduate students or undergraduate students?
Yeah, I have a naive question. Thank you for your interesting talk. Before you have mentioned even though it's GRMHD or maybe modify the GRMHD, it doesn't change much as long as we impose the continuity condition, right?
Did I say that? Is that the question?
Yeah, no. Yeah, my question is, what about the case when we move to the post-Newtonian limit? I mean, just if we just do MHD in the Newtonian mechanics, can we still reproduce the light ring? Around.
Okay, so I will try to answer in two parts. One is what I said is that when we do analytical interior models and connect it to GRMHD, or just take some density velocity profiles and do analytical models, that part we can do in GR and non-GR spacetimes. The non-GR full MHD simulations are basically non-existent. They are only for metrics that you practically can't tell the difference from Kerr metrics. So fully numerical answer to that question, we don't have one yet. But what we can say is that changing the space-time and changing the plasma under these reasonable assumptions doesn't increase the uncertainty beyond what we had already allowed for, that bias between the peak of emission and the shadow size. The second part of your question is, how different are we from Newton? And one of the frameworks in which you can test that is, of course, these post-Newtonian parameters, which in the solar system we use, in the pulsars we use them. And what we did in our recent PRL paper is take these constraints, if I can find them, take these constraints that we obtained directly on modified Kerr metrics and do a post-Newtonian expansion so that we can basically say how different from Newton, how different from GR, and how different from solar system tests. So of course, I mean, the GR, the leading order GR term is there, we are able to constrain, for example, the 2PN order with these metric tests.
I had a question about the Sagittarius A star. So you said the time variability was on the time scale of minutes or so at the worst. But so would you still be able to make some sort of time averaged image, or are there more fundamental problems due to the time variability of the image?
So the time scale on Sag A star is anywhere from minutes to multiple hours. We don't know the spin. And the reason why it's difficult to average images is, in general, is because when you do the Fourier transform and take the amplitude, it's no longer a linear transformation. So averaging the images and doing the Fourier transform versus doing Fourier transform of individual snapshots and averaging them don't give you the same answer. So very generic reconstructions, if you know nothing about how your plasma is moving, and if it really has these large fluctuations, that would not be a solvable problem. Luckily, that's not what's happening. There is a noise budget. There are potentially some morphological changes in ways that we expect from simulations, but we are not completely in the dark as far as, oh, well, if it's like changing from minute to minute or hour to hour, how do we use visibilities to disentangle that?
Mm-hmm. Thank you. More questions for Feryal?
If you think of something later, feel free to send me an email. I'll be happy to keep discussing afterwards.
Well, I will stop the recording then, and thank you again, Feryal, for a beautiful talk.
Thank
Thanks
you
so much.
No, thank you for